Okay, so today we had some troubles with the video in class, so I'm going to redo the first part of the lecture for you now. We're talking about two force members, and to talk about this, there's a sample problem in the book where we've got this brake, or a lever kind of, that comes down, and it's pin connected at the bottom, and then it's got a link that's kind of rectangular shape, like this, that's pin connected as well. Now, if I asked you to draw a free body diagram of this little guy that's a rectangle, what we would do is we'd pull him out, and it looks something like this, right? We pull it out from its surroundings, and then we'd put the two forces, and we'll call this A and B, and we'd say, well, they're pins, and pins restrict motion in X and Y, and so therefore there's going to be both a horizontal and a vertical reaction at each location. Right? This is what we would expect if we drew this free body diagram of this guy. Now, let me see if I can get a little bit better focus for you here. So the reality is, right, if we call this B sub x and this B sub y, and this A sub x and A sub y, that really we could have some resultant force that's the combination of these. So maybe B sub x goes off in this direction, and this would be the force B, and maybe A goes off in this direction, and that would be the force A, right? Now, let's think about that for a second. If we draw him again, we're going to draw this over and over as we do this. Let's say that we ended up and we just said, well, maybe the forces are such that F sub B goes straight up and F sub A ends up horizontal. So essentially we're saying that AY is 0 and here BX is 0, and so we end up with this little drawing here. So my question to you is this in static equilibrium right now? If these two forces, F sub A and F sub B, were acting on this link, would it stay in static equilibrium? Think about that for a second. So it wouldn't, right? And one of the ways we could see that is that if we sum the forces in the x direction, right, we're going to have F sub A. And assuming that F sub A is a non-zero number, then we're going to have some acceleration, and it would not be equal to 0, which is what we require for static equilibrium, is that the sum of the forces in a general direction be 0. Okay? So let's redraw it one more time. What if, to fix that, what if we make the forces equal and opposite? So I'm going to redraw it over here. And what if I say, okay, well, let's make F sub B still go straight up, and F sub A go straight down. And I'm going to tell you that F sub B is equal to F sub A, or the magnitudes of them are equal to each other. Now are we in static equilibrium? So think about that for a second. If we sum our forces in the y direction, right, we're going to have, and let's assume up is positive, we're going to have F sub B minus F sub A, and that indeed does equal 0, right? So is it in static equilibrium? It's not in static equilibrium, because if I sum the moments, maybe I'll sum the moments about A, right? Say counterclockwise is positive. I will have this distance D, right? So I'll have F sub B times the distance D, and that will not equal 0, right? So in order for static equilibrium to be true, we always say that the sum of the force vectors has to be 0, as well as the sum of the moment vectors equaling 0, okay? This is the conditions of equilibrium for statics, which is what we're talking about. So let's draw this guy yet again and say what condition has to be true if I'm going to apply a force here and a force here at A and B, what has to be true in order for that, if the forces are non-zero, what has to be true in order for it to be in static equilibrium? Is there any way that we could do this that would cause it to be in static equilibrium? There is, and it is if we put the forces along the line that connects A and B. So perhaps my forces end up looking like this. F sub A is down and to the right, and F sub B is, F sub A is down and to the left, and F sub B is up and to the right. And in this case, now if I sum my forces in the X, if these guys are equal, they're going at the same angle, so we'd have, let's call it theta and theta. So in the F sub X, I'm going to have F sub B cosine theta minus F sub A cosine theta equals 0. Well, indeed, that's true. F sub X would be the same. And if I sum my moments, where should we sum our moments about? Let's sum them about A. Okay. Well, what's the lever arm for F sub A? It'd be 0. And the lever arm for F sub B? Also 0, because the line of action passes through A. So the sum of the moments is 0. Right? Similarly, if we chose another point here, C, and we summed the moments, we'd have to find that perpendicular distance that I'll call D. But still, I'd have F sub A twisting it counterclockwise, and I'd have F sub B twisting clockwise. Okay? So what happens in two-force members, I want to develop now kind of our definition of a two-force member. A two-force member which we're going to find as having two force application locations and I should say, sorry, for a two-force member, which I'm going to tell you is any member that has two force application locations. So what I mean is two places where forces are applied. So in our example, it's A and B, right? If we look up at the lever arm here for this guy, is that a two-force member? It's not, right? Because actually I left something off. But here there's force application down at the bottom. Sorry. There's force application at the link. And there's force application where you pull on the lever. So there's 1, 2, 3 spots of force application. So this is not a two-force member. So if we have a two-force member, it's more like the link here where there's just at A and at B. So a two-force member, which means two force application locations, for it to be in static equilibrium, the forces must be equal and opposite and act along the line connecting the 2 points of application. Okay. So let's look at some examples from the book here and identify whether they are two-force members or not. Okay, so I love this chapter because there's all sorts of interesting, very applied things. We end up using two-force members in tons of places because they're very, very useful. All right. So let's look at this crane. We did a problem similar to this the other day. We don't really need to look at the problem, But if you just look at the picture, okay, the boom of the crane, which I'm going to say goes kind of down here from the pivot point all the way up to the load up here, would that be a two-force member? And you have to notice that it has this G2, so we must assume that the problem is telling us that it has some mass that's located there in the center. So the way we determine is it two-force member or not is how many places is a load applied. So there's a load at the end, there's one force location, there's its own mass, there's a second force location, there's this hydraulic ram that moves it up and down, so that'd be a third force location. And then down here it's probably pin connected, so it has a fourth location. So that is not a two-force member. There is a two-force member in this problem though. If we look here, right, at the hydraulic ram, it's going to be pin connected at the bottom and pin connected at the top. So it is a two-force member, right? It's got force that just runs along it. So why is that helpful for us? Well, because now, if I were doing the free body diagram of this boom, I would have a pin down here at the bottom. So pins, remember, would have a force in the X and the Y. And then I'd have another pin here where the hydraulic connects, and that would have a force in the X and the Y. And so I would have four unknown forces there, but because I know that it's a two-force member, I know the direction of this force, right? It has to lie along that hydraulic ram, and therefore the only thing I don't know about the force here is its magnitude. Okay? Let's find another example. How about this guy, the old ball and chain, right? Okay, so it's a simple kind of boom. Here we see two pin connections. So if we're asked in the problem to find the reaction at A and C, and typically if it's a pin, we'd say, well, there's an X and a Y component to that, right? So both A and C would have X and Y components. However, because if we look at C, it only has a load at B and a load at C, so that becomes a two-force member. What about AB? Also, it doesn't say anything about the weight of the boom, so we're assuming it's weightless. Then A to B would also be a two-force member. Okay, let's look over at this boom here. Is this a two-force member? Think about how many locations of force application are there on this guy? Okay, it's not, because there'd be a force application at A, at D, and at B. So here there are three forces, so this is not a two-force member. What about the cord going from B to C? Force applied at B and at C, and nothing in the middle. So yes, BC is a two-force member, and because we're told the geometry of that cord, we know the direction of the force. Okay? All right. So if you want to turn in your note packet now, we'll do the example that's right on the front page there of the airplane landing gear. Sorry, I'm trying to get this zoomed back up for you. Okay. So in the airplane landing gear, we have this wheel. Okay. And as the plane lands, it applies a force of, is it 2 kilonewtons, I believe? Yeah. 2 kilonewtons in this direction, and a normal force of 6 kilonewtons in the vertical direction. And this is the front nose gear on a plane. And it goes up here, and it's pin connected to the plane. And then it's got a strut that comes back here, also pin connected to the plane. Okay? And we're told that the distance didn't draw this quite to scale, here is 0.6 meters, and this distance is 0.4 meters. The angle between these is 30 degrees, and the angle of the main strut with the vertical is 20 degrees. Okay? And so this is our given. And we're asked to find, let me put some letters on here, and I want to make sure I match them to what your notes say. So A, B, C, A, B, C, and I'm going to call this D. And we're asked to find the loads at B and C, right? Okay. So this is how we're going to approach this problem. Let's draw the free body diagram of DC. So here's our free body diagram. At D, we know we've got 2 kilonewtons horizontal, 6 kilonewtons vertical. We then have CY, CX, and at A, it's pin connected. So we should say, well, we'll have AY and AX. But this looks like we have 1, 2, 3, 4 unknowns. It's a two-dimensional problem, so we only have 3 equations of equilibrium. So technically, before today, we would have said that this is unsolvable. But if we look at member AB, how many force application locations does it have? At B and at A. So this is a 2-force member. What about CAD? There'd be 1 here, 1 here, and 1 there. So CAD is not a 2-force member. It'd be a 3-force, or it just doesn't matter. The main thing is it's not a 2-force member. Knowing that AB is a 2-force member, though, remember our definition that for a 2-force member to be in static equilibrium, the line of action of the forces has to lie along the point that, or the line that connects A and B. So we know that instead of having AY and AX, we actually just have the force A that goes up and to the right. Okay? At what angle? Well, at 30 degrees off of this guy. All right? So now we can solve this problem. Let's do sum of the forces in the X equals 0. So the sum of the forces in the X, it looks like I'll have CX plus the component of FA that's in the horizontal, so that'd be plus FA. And if that's 30 and this is 20, I'm looking for this direction of it, I'm going to say sine 50 degrees, right? 30 and 20 is 50, and I'm looking for the opposite, which would give me the horizontal. And then plus 2 kilonewtons has to equal 0. We'll do the same thing then, sum of the forces in the y direction has to be equal 0. So in the y direction, I'll have 6 kilonewtons plus FA cosine 50 plus CY equals 0. And then if I sum the moments, I can sum the moments about any point that I would like. I'm going to go ahead and choose this point, though, so that I don't have to do trig for these other guys. So I'm going to sum the moments about A and set that equal to 0. Okay? So if I sum the moments about A, remember that we had 0.6 meters here. So it looks like 2 kilonewtons times 0.6 meters, right? Looking at our drawing, 6 meters is the lever arm to point A, or 0.6 meters. And that's going to go in the counterclockwise direction, so it's positive. That'd be minus, though, 6 kilonewtons. And I need to figure out what this distance here is. What's this guy? Okay, what's this D? And doing some trig, I know this is 0.6. I can figure out that the tangent of 20, let's see, tangent of 20 would be equal to the opposite, D, over the adjacent, 0.6. Or 0.6 tan 20 is equal to D. Okay, so I'm going to put that down here for my lever arm. That would be 0.6 tan 20. And then we need to do cy and cx. So cy, or let's do cx first. Cx is going to be negative, so minus cx times the distance, 0.4 meters. And cy, that's going to be a positive, right? So it would be positive cy times, same idea, 0.4 tan 20 equals 0. All right? And now we have 1, 2, 3 equations, and we can solve for the unknowns, which are cx, cy, and a. And what I got for those are negative 2.66 kilonewtons, negative 6.56 kilonewtons, and 864 newtons. Okay? So you can see from going forward, being able to identify these two force members is going to be critical to being able to solve problems like this. All right? Okay, from this point on in the lecture, we were able to capture it, so I'm going to stop here and let you catch up that video. It's going to be separate, and I will get your homework here posted shortly. Thanks so much.